Basic characteristics of a DC motor. The equivalent circuit for separately excited DC motor is as shown. When a separately excited DC motor is excited by a field current IF and armature current IA flows in the armature circuit, the motor is going to develop a back EMF and torque to balance the load torque at a particular speed. The field current IF of a separately excited motor is independent of the armature current IA, and any change in the armature current has no effect on the field current. The field current is normally much less than the armature current. The equation describing the characteristics of separately excited DC motor can be determined from the figure. Then the instantaneous field current IF is described as the VF equals to RF IF plus LF d IF by dt. This equation is from the field circuit. Armature current can be found from the equation VA equals to RA IA plus LA dIA by dt plus motor back EMF EG. EG is also known as speed voltage, is given by EG equals to kV omega IF. The torque developed by the motor is given by TD equals to KT IF IA, where kV is the voltage constant, KT is the torque constant. The developed torque TD must be equal to load torque TL. Then TD equals to J d omega by dt plus b omega plus TL. Usually torque is represented with the tau, but here I'm just considering that as a T. It's not standard notation. Okay. Under the steady state condition, the time derivative in this equation are 0. Then the steady state average quantities are, in all these 5 equations, derivative terms equals to 0. Then we are going to get VF equals to RF IF, equation 1, EG equals to kV omega IF, equation number 2, VA equals to RA IA plus this term will become 0, then EG that equals to RA IA plus kV omega IF, that is equation number 3. Then TD equals to KT IF IA, which equals to, in this equation this term will become 0. B is the viscous friction constant omega plus TL, that is equation number 4. Then the power developed is given by PD equals to the torque developed multiplied by the motor speed omega. The relationship between the field current IF and the back EMF EG is nonlinear due to the magnetic saturation. These are magnetizing characteristics. From the equation number 3, the speed of a separately excited DC motor is given by omega equals to VA minus RA IA divided by kV IF, which equals to VA minus RA IA divided by kV VF by RF. That is equation number 6. From this equation, the motor speed can be varied by controlling the armature voltage VA, known as voltage control. One is the voltage control by varying VA. The second one, the controlling the field current, known as field control. And third one, torque demand, which corresponding to the armature current IA for a fixed IF. The speed, which corresponding to the rated armature voltage, rated field current, and the rated armature current, is known as the base speed. And these are the characteristics of separately excited motor. First one is speed versus torque developed and power developed. And second one is speed versus the armature current and the field current. So this is the reason where the torque is constant, and this is the reason where the power is constant. In practice, for the speed control less than the base speed, where IA and IF are constant, so we need to go for the voltage control. The speed is higher than the base speed, the armature voltage is maintained at the rated value, and the field current is varied to control the speed. However, the power developed of the motor is going to remain constant at this region. The field of DC motor may be connected in series with the armature circuit as shown here. And this type of motor is called series motor. The field circuit is designed to carry the armature current. Then the steady state average quantities are now will become Eg equals to kV omega IF equals to Ia, so Ia. That is equation number 7. Va equals to the resistance Ra plus Rf of Ia plus Eg. Let this be 8. Substituting the value of Eg, you are going to get Ra plus Rf Ia plus kV omega Ia. Let this be 9. Now, the torque developed Td is given by the torque constant Kt Ia If. That is equation number 10, which equals to the B omega plus TL. This is equation number 11. Now, the speed of the series motor can be determined from equation number 9. Omega equals to Va minus Ra plus Rf Ia divided by kV Ia. That is equation number 12. Now, from this equation, the speed can be varied by varying the armature voltage Va, there is voltage control, then the armature current Ia, which is a measure of torque demand, and equation 10 indicates that a series motor can provide the high torque, especially at the starting. This figure shows the characteristics of a DC series motor. For a speed up to base speed, the armature voltage is varied and the torque maintained constant. So, constant torque mode. Once the rated armature voltage is applied, the speed-torque relation follows the natural characteristics of a motor. That power remains constant. Thus, constant power mode. As the torque demand is reduced, the speed increases. At a very light load, the speed could be very high and it is not advised to run a DC motor without a load. This is regarding the basic characteristics of a DC motors. There is separately excited DC motor as well as series motor. If this video is useful, please like, share and subscribe. Thank you.